what happens in the previous laboratory. So the main objective there is to fine-tune the pre-trained text classification models, Distilbert. So what we did is we use a pre-trained transformer model instead of building a neural network from scratch. Fine-tune Distilbert for a text classification task. Use the Hugging Face Transformers ecosystem. Prepare text using tokenizer. Train a classifier using PyTorch. Evaluate predictions using accuracy and other metrics. The task is classify recipe titles into fruit and label it to 0, vegetable and label it to 1. So example, the recipe title is banana smoothie and the label is fruit and index value is 0, and garlic roasted broccoli is labeled as vegetable, which is 1 value is index. So why we use a pre-trained model? So in our previous discussion, we built everything manually, like vocabulary, tokenization, embeddings, neural network layers, padding logic. That works, but it has limitations. We need more data. We need more training time. Learns language from scratch. Usually performs worse. Now you use transfer learning. Transfer learning means you start with the model that already learned language patterns from massive datasets. Instead of teaching the model English from 0, you only adapt it to your specific task. What is Distilbert? Distilbert is a smaller and faster version of BERT. BERT is a bidirectional encoder representations from transformers. Distilbert keeps most BERT's language understanding ability while being lighter, faster, using less memory. It already understands grammar, sentence structure, context, relationships between words. We only fine-tune it for recipe classification task. So the first step is we import we need it. It's like random, numpy, pandas, scikit-learn, compute class weight, torch nn, utility data, and transformers. We import importing libraries is we use tensors, neural networks, training, gradients, GPU support, and the transformers is from Hugging Face, provides pre-trained models, tokenizers, transformer utilities, and data loaders efficiently loads training batches, dataset custom PyTorch dataset class. Compute class weight, it handles class imbalance. If one class appears much more than other, the model may become biased. Next is random seed. What is seed? Like for example, we have the seed equivalent to 99. This ensures reproducibility, meaning same shuffling, same initialization, similar outputs across runs. Without seeds, training changes every run. Next is device selection. We select the device that we in the training. Like if GPU exists, we use the CUDA. Otherwise, we use GPU. GPU massively speeds up deep learning. Next is load dataset. This is step 2. We load the recipe data in the pandas. Label encoding. We label it to 1 and we label the fruit into 0. Machine learning models cannot understand text labels directly, so we numerically label it. Fruit is 0, the vegetable is 1. Label encoding, cleaning missing values, removes rows with missing recipe names. Models cannot process empty text. Extract inputs and targets, text, and labels. Now we use that toList both in the text and the labels. So it contains recipe titles, labels can contain specifications, and we set the text into 0 index, banana bread, like example, and labels 0. Understanding the tokenizer. One of the biggest ideas in transformer is tokenization. Neural network cannot understand raw text, so text must become numbers. Distilbert has its own tokenizer. From transformers, import Distilbert tokenizer. What does this tokenizer do? The tokenizer splits text into tokens, converts tokens into IDs, and add special tokens, pad sequences, creates attention mask. Example, if we input the fresh apple pie, it may become having a 101 fresh apple pie, and in the end is 102, actually converted into integers ID. I guess specialized tokens. Transformers use special markers. Like if we have CLS, its meaning is classification token, SEP is separator token, and pad is padding. The CLS token is especially important. The model uses its final representation for classification. Padding. Sentences have different lengths. Example, apple pie, extra crispy garlic roasted broccoli. They are different lengths. So the neural networks need equal tensor sizes. So shorter sequences are padded. Example, 101 to 1000 and 3000 to 102, and all values of 0, like in the end, where 0 is padding. So to make uh, to make them equal tensor sizes. Next is the attention mask. The laboratory also creates attention mask. This tells the transformer which tokens are real, which tokens are padding. So if we have the input IDs like 101 on 2000, 3000 to 102, and 0 and 0, those 0 values is the are padding. So in the attention mask, we could convert the value of 1, which is the real token, and if the padding is equivalent to 0. The model ignores padding positions. Next is loading Distilbert. The notebook or laboratory Distilbert model or Distilbert for sequences classification depending on implementation. So pre-trained weights from Hugging Face. The model already contains language knowledge. Next is fine-tuning. Fine-tuning means continue training a pre-trained model on a smaller specialized dataset. The original Distilbert learned general English. Now we adapt it for recipe title classification. So here's the important concept in embeddings. Transformers models convert tokens into embeddings. Embeddings are dense vector representing meaning. So the example idea is apple is a vector, banana is a vector, carrot is a vector. Words with similar meaning have similar vectors value. Next is transformer encoder. Distilbert mainly uses self-attention. Self-attention allows words to understand context from other words. Example, if we have the sentence apple pie with cream, the word apple can attend to pie, cream, to better understand meaning. Why attention is powerful? Old RNS process words sequentially. Transformers process words in parallel. The advantages is faster training, better long-range understanding, stronger context learning. Next is dataset class. In the laboratory, we build a custom dataset class. The purpose is to provide tokenized data to the data loader. Usually contains length and get item. So as get item returns one training sample. Usually the input ID is attention mask and label. Next is data loader. Creates many batches. Instead of training one sample at a time, batch size is equivalent to 16. Okay, for example, the model trains on 16 samples together. Benefits is faster, more stable gradients, GPU efficient. Train and validation split. The data set is split into training data, validation or testing data. Training data updates weights, validation data is measured as generalization. Next is loss function. Classification usually uses cross-entropy loss. Cross-entropy compares predicted probabilities, actual labels. So lower loss, better predictions. Understanding logits. Transformer classifiers output logits. Logits are raw prediction scores. Example, negative 1.2 and 2.7. So after softmax, it will become 0.02, like for example, and 0.98, meaning 98% confidence for class 1. Next is optimizer, usually Adam. This updates parameter using gradients. And gradients. During training, During training, we have the forward pass, next is compute loss, next is backpropagation and update weights. So backpropagation computes gradients. Gradients measure is how much each parameter affects loss. Next, fine-tuning updates all parameters. A major difference from feature extraction. During fine-tuning, transformer weights also updates, meaning the pre-trained model adapts itself for recipes. Training loop. The typical structure is we use the for loop epoch in range in number of epoch. So each epoch model the train 0. Next, forward pass, compute loss, backward, optimizer step, and evaluate. What is model the train? Enables training behavior important for dropout and batch normalization. Model that eval. Use during evaluation, disables dropout randomness, ensures a stable prediction. Next is torque.nograd. During evaluation, Lograd disables gradient tracking. This benefits less memory, faster inference. Next is dropout. Transformers often use dropout. The purpose is to reduce the overfitting. It randomly disables neurons during training. Next is overfitting. Overfitting means the model memorizes training data but performs poorly on new data. Fine-tuning can to overfit if the dataset is small, too many epochs, evaluation metrics. So in the laboratory, evaluates the predictions. So the common metric is the accuracy, meaning the overall correctness. The precision is correctness of positive predictions. Recall is ability to find positives. F1 score is balance between precision and recall. Next is inference. After training, you can input new recipe titles. Like for example, if you have strawberry banana smoothie, the model predicts fruit. Next is Hugging Face ecosystem. One of the biggest lessons in the laboratory is Hugging Face simplifies many difficult NLP tasks. Instead of manually building vocabularies, embeddings, tokenizers, transformers, we just can from pre-trained model function and use the state-of-the-art models immediately. What is the key difference from the previous lab? So the previous lab built classifier manually, simpler architecture, learned embeddings from scratch, and this lab uses pre-trained transformer, uses transfer learning, much stronger language understanding, and less manual NLP engineering. So the important transform concept to remember is tokenization. It's from the raw text into tokens into IDs. Attention mask, it tells model which tokens are real. Embeddings is this vector meaning representations. And next is self-attention. Model learns context from the other words. Next is fine-tuning, adapt pre-trained weights to new tasks. Next is transfer learning, reuse knowledge from massive pre-training. And logits, raw prediction scores. And next is backpropagation, is gradients, update weights. So why this approach is powerful? Using pre-trained transformers gives better accuracy, less data requirement, faster convergence, stronger language understanding.